So in the morning section, I think the explanation about how to find a Nash equilibrium that's not an SPE is not very clear. So I'm going to redo that thing with the Joker example. Hopefully it gets better. So the first thing you always do is find the SPE. So when we find SPE, you start from the smallest sub game. So this is the Joker's choice. So I'm comparing two of Joker's payoff. So 0 and 1. 1 is larger, so I highlight the larger action. The second thing we do is the second smallest subgame, where player 2 compares if I choose not to kill, I get 0. If I choose to kill, because we are finding SPE, so we need everyone to do their SPE action, so we will assume Joker will kill. So when P2 chooses to kill, then I follow the path, and then I get -1. So compare 0 and -1, I choose 0, so that's why I highlighted this one. And similarly, we go back to the start. For player 1, if I choose not to go, I get 0. If I choose to go, again, I follow the equilibrium path, so it's go and not kill, so I get 1. So comparing 0 and 1, I choose go. So that's the first step. Always find the SPE first. And then the second step, I said there are two ways of finding a Nash. I mean, not really finding a Nash. There are two ways to find a Nash that's relatively close to the SPE. So the only way to find all Nash equilibrium of an extensive form game is converting it into strategic form, which you see at the end is very hard to do. So I'm not going to do that. And here, the first way to do is changing something that's off equilibrium path. So one thing that I think people are confused is what is equilibrium path. So to find equilibrium path, we start. So equilibrium path is also called equilibrium outcome. So I think that start part is actually useful because on the exam I wrote equilibrium outcome. So you always start at the beginning, start at the root of the tree, and then you follow the the actions, you follow the equilibrium actions, you follow the path, that's called equilibrium path, and then you reach some version of the end of the game, and that one is called the outcome. Or, or the whole path that leading to this is called the equilibrium path, as I said in class. So the action here, so everything that's not on the path, so for example here, would be an off equilibrium path. So, and as I said, the first way to find a Nash is change things off equilibrium. So if I do that, I can change from kill to not kill. And if it does not change the equilibrium path, then it's okay. So what we need is we needed to not change the equilibrium path, not change the equilibrium. So when the Joker does this, so basically Joker moved to here, and then I want to check whether player 1 and player 2 has incentive to change as well. But player 2 does have incentive because player 2 choosing not will give him 0 and choosing kill will give him 1. So 1 is better. So it does lead player 2 to change to kill. So that's not a Nash. So this is not a Nash. So basically, I would say Joker changing from kill to not kill is not a Nash. And the second way to do it is change on equilibrium. On equilibrium. So what that is I either change player 1 from go to not go, which I didn't say in class. If I change the first player's action, it will not affect anyone following him, so that does not work. So change on equilibrium means change the action of the second player, so I can only change from player 2 from not kill to kill, because that will actually affect the action of player 1. When player 1's action changed, it does not affect action of player 2, so that's important. And so the only choice is change player 2, so we player 2 we can change from not kill to kill, and let's check whether that's a Nash or not. So the requirement is if we change something on equilibrium, we need the equilibrium to change. So we need change equilibrium. So I basically want the first person to change from go to not go, and that's actually the case. So if I change from not go to go, let's see what's happening with the first guy. So if I choose not go, I'll get 0. If I choose to go, then I will follow the new path. So let's actually highlight the new path because I changed from not to go to go. So starting from P1 and then I follow the path I get here, I get -1. So I'm comparing 0 and -1. So 0 from not go, -1 from go. So obviously I will switch to not go. So then that Nash equilibrium is like this. So all the green ones combined is a Nash equilibrium. And let's write that down. So it's not go, kill, and kill.